So what's controlling it? Well, a big part of it is the age of that lithosphere that's subducting. Older oceanic plate is denser and sinks more rapidly. So if you have a subduction zone with very old oceanic plate as the leading edge, it's going to sink more rapidly, more rollback, steeper angle, than if you have oceanic plate that's younger but still subducting. So, just to throw out some numbers, if you have 200 million year old oceanic plate versus 100 million year old oceanic plate, that 200 million year old plate is going to be thicker and denser and therefore sink more rapidly, have more rollback, have a steeper angle than that 100 million year old plate will. Also, the convergence rate gets controlled by the rate of slab pull and ridge push. So if you have much older plate sinking more rapidly, that's more slab pull, that's going to increase the convergence rate. Also, if you happen to have more ridge push because of the mantle conditions, that's going to increase the movement speed and therefore increase the convergence rate. Now, that downgoing plate is much cooler. That's why it's going down. It's cool, it's dense, it's sinking into that hot mantle because it has negative buoyancy. It is more dense than that hot mantle. However, you take something cold and you stick it into something hot, it starts to warm up. So that downgoing plate, although it's cooler, is going to start heating up. It's made of rock. Rock is not a very good thermal conductor. That's a good thing for us. If rock conducted heat very, very well, like a piece of steel or a piece of copper does, one of two things would be going on. Either the surface of the Earth would be so hot because all of that heat conducting out of the core that we would just cook and die, or it would have conducted all of that heat out ages and ages ago, then cooled off, and it would be too cold on the interior of the Earth to have plate tectonics, to have a magnetic field, and therefore we wouldn't be alive. So it's really good that rock is a poor thermal conductor. This is what allows the crust to basically insulate the interior of the Earth and allows us to still have plate tectonics, allows us to still have a molten core, that allows us to have a magnetic field, which allows us to have life. So we can be here talking about how rock is a poor thermal conductor. So as it's subducting, again, this is the whole lithosphere. It's pretty darn thick, tens of kilometers thick just for the crust, 600-ish kilometers thick for this lithosphere. Not 600, about 400 down to that transition zone. So hundreds of kilometers thick, subducting. Yes, it's going into extremely hot mantle, but the center of that is, a minimum of 100 kilometers away from that hot mantle. It's insulated pretty darn well. So it's going to be the coolest. As you get closer to the edges of that downgoing slab, it's heating up from that mantle material that it's sliding through and from the stress and compression. So the edges of that downgoing slab, eventually start to approach the temperature of the mantle material. The interior is still much cooler. As the temperature and pressure change, the oceanic crust ends up more dense. Not because the temperature is increasing, but because the pressure is increasing. The temperature is increasing more slowly than the pressure. So its density is getting greater as it's going down, which increases the gravitational pull, pulling it down faster and faster as it gets deeper. This causes an issue. You think about the top is going down at one speed, the bottom is going down at a greater speed. Sure, you have some rollback as the angle's changing, but that can only do so much. The leading edge of it will eventually break off. And this does happen. So, this is a black and white picture. I have a color one coming up, showing you the general thermal profile. So, up at the surface we have ocean temperatures. Bottom of the ocean is basically pretty darn close to 0 degrees Celsius. Often at like 1 degree. Get down a little ways into the crust and it's much hotter, 400 degrees Celsius. Down into the crust and lithosphere, increasing temperature as we move down, 400, 800, 1000, 1200 degrees Celsius, and then we're getting into the mantle. So basically at the bottom of the crust, bottom of the lithosphere, so at the bottom of the plate, it's at right about 1200 degrees Celsius. Down into the mantle, even higher temperatures, 600 degrees Celsius and higher. So this plate that had this thermal profile gets shoved down into that mantle, and we get heating. The heat transfers into it from both sides because it has mantle material below it and mantle material above it. And the temperature profile is not equal because the bottom of that plate started out much hotter. It started out at 1200 degrees Celsius. So that 1200 in contact with that 1600 doesn't have to heat as much as the top side that was 0 degrees. Even if we don't show that 0 degrees portion of it, and we have that 400 degree isotherm. Isotherm is a term for the line that shows you where that temperature is. It's basically a contour line, like on an elevation map, except this time it's a temperature contour line called an isotherm. So that 400 line is curving down and doesn't get very deep because it's being heated up. But you notice it's kind of squished up towards the top of the plate. Same with this 800 and the 1200 line, or the 1000 and the 800 goes off the bottom of the page. They're closer to the top of that plate. So the top quarter is kind of the coolest portion. And we can see here, this is a phase change curve. It's not a straight line because it's both pressure and temperature that matter. And so less pressure, less temperature, or more pressure, more temperature causes the same result. And this is where olivine changes into spinel. Here we can see, it's in French, but we can see it's the same thing. So we have the downgoing plate. We can see the isotherms squished towards the top of the plate. We've got a little volcanic arc. Here is that olivine to spinel line. And much deeper, that spinel is then going to change into oxides. So the same material in this downgoing plate is going to phase change twice, purely because of temperature and pressure. No chemical changes, just pressure and temperature changing what form of mineral it's in. The earthquakes that happen, again, remember this is the Wadati-Benioff zone, showing earthquakes, showing us where the plate is. We get different types of earthquakes at different points along that downgoing plate. In some places they're tensional, some places they're compressional. Geophysicists can tell which kind of earthquake it is based on the types of waves that come off, which they pick up at the seismic stations around the world. So we can see these white circles are tensional. The black circles represent compressional. So we have an area of tensional stress. This is where that flexure is causing extension on the top edge only. It's like if you take your credit card and you bend it, right at the top of that bend you can see little cracks, if you bend it far enough, little cracks opening. There's extension because of the bending. Then, right below the overriding plate, we have compression. This is because it's getting jammed against that plate is pushing against it, there's a lot of pressure. We get below that, so that we're past that friction, past that pressure. This is an area of tension again, because remember, the deep part of that subduction plate is moving faster because as it got deeper, its density increased and it's pulled down more rapidly. So that's causing this area of tension here, below the overriding plate, so away from that tension or that compression and extra friction against that plate. Down here it's sliding through the mantle more easily than it slid past that. Still not easy. I mean, it's still going through rock, but it's through softer, hotter, more plastic rock. So here we have tension because this deep part is moving faster. But this leading edge area has compression again because it's trying to push its way through mantle material. It has to push mantle out of the way to subduct. So the leading edge has compression. Behind it there's some tension. Back up where that overriding plate is in contact with the subducting plate, compression. And then behind that, behind the trench, where we have that bulge forming, we have tension. So I was talking about the pieces of that subducting plate, the ends of them going faster because of being denser. Well, they do break off. Two different ways that it can happen. One is we see here, they actually just kind of stretch and pinch off and then sink down and end up at the core mantle boundary. They can't sink into the core itself because as a different material it has a much higher density, therefore they will not sink into it. Or they can kind of start melting and becoming more plastic and misshapen, and kind of blobs break off rather than rigid pieces breaking off. A lot of this depends on how much water content and exactly how much sediment is trapped with it, so what the total makeup of that subducting plate is. whether it's going to stay rigid and solid, whether it's going to start melting, plus if it happens to be going along, right along or through a hot spot in the mantle versus cooler parts of the mantle, that'll help decide whether it melts or not as it's going down. Either way, it's still cooler than the rest of the mantle. It takes time, millions and millions of years, for that rock to heat up completely to be the same temperature. It's very loosely similar to if you've ever seen a lava lamp, where you have the globs of material going up and down in the fluid. That can happen very quickly because the materials conduct heat a lot better, and they're moving it through liquid rather than through solid rock. But the same general principle, after it reaches the bottom, it takes time to heat up again before it can start moving and gaining positive buoyancy. The heat source in this case is the core. The core is hotter than the mantle, therefore as they sit along the bottom of the mantle, along the outer surface of the core, they're heating up. So, looking back at trenches. Trenches are the boundary of the downgoing slab and the accretionary prism of that overriding plate. They're right between that downgoing plate and that accretionary prism. That low spot is what the trench is. All of these trenches are going to contain some sediment. Because it's sediment in a trench, we call it trench fill. I mentioned this briefly before. Just reiterate, and we can see this dark curved area here is a trench. There's another smaller, shallower trench between, and another one here, another trench here, and a trench here. At every place that there's subduction, there is a trench. A lot of the sediment fill is from turbidites that go rushing down that accretionary prism. Submarine canyons form due to water disturbances, earthquakes. You've got wet sediment, it's under the ocean, and it gets disturbed, and you get these turbidites rushing downhill and dumping stuff into the trench. Now, the accretionary prism itself, so far we've shown them pretty simplistically, just kind of a little fan-shaped thing, and said, hey, it's the accretionary prism, it's sediment scraped off of the subducting plate. There is more to it. It is created from the shear between the two plates, so as this plate subducts, this ocean bottom sediment is scraped and piled up into this accretionary prism. As it does this, not only is it built up, but there's deformation that happens. There's a lot of pressure involved. There's a lot of faulting involved. And there's even heating involved. Now, it's mostly pelagic sediment, but some basaltic material gets scraped off and mixed in with it, and this affects what you get as it gets metamorphosed. Say, wait, metamorphosed? Who is saying anything about that? Well, I just mentioned pressure and temperature from the scraping and buildup. Therefore, it's not surprising that we're going to get metamorphism in parts of that accretionary prism.